Hey, buddy, this is Rohit Agrawal, and we are here at Astrophysicist podcast. We have today with us Shweta Ramkumar, who is a science communicator with us, and a special guest, Debarati Chatterjee, who is Chairperson of Outreach at LIGO-India and Associate Professor at IUCAA. Hello, Debarati, ma'am.
Hi, it's my pleasure to be here with you too.
First of all, thank you very much to, join us. You must be very busy, so it's really great, and I'm honored that you've actually taken time out of your schedule to do this with us.
Thank you very much for connecting with me. It's true that I have a very busy schedule.
Yeah.
That's because you can say I have 3 jobs right now. So I am an associate professor. I have teaching duties. I am an astrophysicist. So I have to put a lot of time into research. And on top of that, LIGO India is a very exciting upcoming project. And I'm handling education and public outreach, which means a lot of responsibility, and it's almost like a 24/7 job. So it's very difficult for me nowadays to concentrate on my own outreach, but I'm happy to connect with you. I'm happy to connect with young people in general.
Thank you very much for saying that. So the first thing I want to ask is, like, generally when people introduce you, like Professor Debarati Chatterjee, so-and-so, and all of those titles, do you actually, feel overwhelmed rather when you take a step back and look at all the hard work that went into, being at this position where people introduce you in a way you have so many titles? How does that make you feel actually when you think about it?
Like you say, when the climb is the hardest, then the views are the sweetest. It's a bit like that. I'm very proud of the titles I have earned. And yes, I am also happy to share that this has not been an easy journey at all. And probably that challenge makes it all the more worth, because as a woman and in astrophysics, it's not easy. In nuclear astrophysics, it's not been easy. And being a faculty in India has not been easy. None of these have been easy, but I would say that every time somebody has to break the ice, and I'm happy to do that.
That's a nice way of putting it. So, like, what spurred you to enter into this field of compact stars and neutron stars and gravitational waves? Because it's something that's not really common in India, not yet, but now it is upcoming. But as a research field in our country, it's something which is strange, which is very major. So, what kind of led you to this research subfield?
Okay, so actually, so I grew up in Kolkata, and so as a young student, I was very excited to learn about astrophysics. It's a subject that has always inspired and excited me. I guess you too as well. I mean, a lot of people are really very curious about how the universe works and where we come from, where we are going. So I was the same. And then I did attend a few public talks, which really, caught my attention. But the actual journey probably began here in, so not IUCAA, it was in TIFR, so Tata Institute of Fundamental Research. So I was doing a master's in physics at that time, and there was an astrosat workshop, which was a workshop to train the next generation to use the astrosat satellite. And a lot of eminent speakers were there. Some of them are my colleagues now. So Dipankar Bhattacharya, they were like, some of them were the lecturers in those workshops. And I learned a lot about how fascinating neutron stars are, because basically these objects, you can observe them in basically every wavelength. And still you don't know anything about them because they are so exotic. And there's literally nothing there is no end to things you can do in neutron stars, because it is so multidisciplinary. And I always had like kind of difficulty in choosing, like, should I study nuclear physics? Should I study particle physics? And neutron stars is the answer. It has everything you can think of. So it's a subject that continues to fascinate me. And when I started working on them, I also got into learning about gravitational waves. I consider myself lucky in this because exactly at the point when I completed my postdoctoral studies and I was stepping into the field of being a faculty, and this is where gravitational waves were discovered, and the field literally is in boom right now. So I'm very excited to look at the prospects, particularly in India, on these topics.
Yeah,
so this is how my journey began.
Okay. I mean, to give some context to the viewers and listeners, Professor Debarati is, as we all know, she's a theoretical astrophysicist. And so her research basically focuses on compact stars, if I'm correct, compact objects. So I think it's more specific on neutron stars, but not limited just to neutron stars, but mostly that, if I'm right.
Right, you're correct. Yeah, so I work on compact objects which are formed at the endpoint of evolution of massive stars. So basically, neutron stars, black holes, not to that extent, white dwarfs, not to that extent, but then you cannot separate out the compact objects. They are kind of like the end point of what all stars, end their lives in. And I'm particularly also interested in how these objects, which are extremely relativistic, which means that they bend gravity a lot because of their compact nature, because of their massive nature. I am interested to find out their internal composition, their internal structure by observing gravitational waves. So I develop models of their interior, which means it is very multidisciplinary. You have to understand nuclear physics, particle physics, condensed matter, a lot of things to model these objects. And then you compare your model predictions with the observed data to understand what is there inside these objects.
Yeah. So to follow up on that, because we've started with the more science stuff, when you simulate these models, what kind of difficulties do you usually face when you simulate such models? And obviously, also because they're very important, you retrieve important information from them. So from your work, like the models that you've simulated or generated, what important retrieval have you made that kind of could explain something that wasn't previously clear to all of us in general?
Okay, so the main challenge here is that, research, that astrophysics research starts basically where textbooks end. So where theories fail, these are such extreme objects. So neutron stars or these astrophysical systems are in general such extreme objects that they go way beyond properties we can actually even imagine here on Earth. So just to give you an idea, neutron stars, they are so dense. They are the densest forms of matter in the universe. And they are so dense that even a spoonful can weigh tons, like a ship. Okay, so you don't know what happens when you have matter that dense, and on top of that, they are the fastest spinning. They are the most they bend gravity the most, and they are the coldest also. Like their temperatures are such that you can even have superfluids inside. So it's like a very, very exotic system that exists out there, and you cannot go and do an experiment in the lab to say, okay, this is what happens there, because it's way beyond what humans are capable of understanding with our current knowledge of physics, which makes it so exciting to study them. But it's also challenging because you have to go on to explore regimes which have never been explored before. But then every time you have new data, you have every time you see a new system in gravitational waves, it gives us surprises, new things that we have never imagined, and then gives us constraints on these models. So we are learning new and new things every time.
Yeah, that's true. That's very true. But I think I have a follow-up question on that. So when you say that neutron stars are sources of gravitational waves, so you mean that you don't essentially have to look for, say, events such as merging events or collapse of two immensely dense and massive objects. So even individual objects are capable of being sources, providing gravitational waves. So in that sense, how do you actually detect gravitational waves coming from neutron stars, because I assume there has to be some kind of displacement going on because these stars are rapidly rotating. So I assume that there should be something going on with their rotation that creates a displacement, which in turn generates these gravitational waves that we all detect and you detect. So what exactly is that displacement?
Yeah, good question. Let me explain. So you are correct about the fact, I mean, although until now we have all the systems, all the gravitational waves have been detected from neutron stars, which are in pairs. And the reason is that when you have pairs, you have these objects going around each other, they are merging into each other, and this gives out profuse gravitational waves. So this has already been detected. But what is true is that these neutron stars themselves, they are so compact and dense, they bend the curvature of space-time around them. They warp space-time around them. And any kind of perturbation in these systems will give out gravitational waves. The only problem is that they are so feeble, they are so tiny, weak, that until, I mean, you can imagine that when I actually started working on this project as a student, or even I heard about it, this was like 10 years ago. And in the last 10 years, like until 2015, nobody has ever detected them because they are so tiny. It's like the amplitude is like 1 part in 10 to the 24 zeros. So you can understand, it's like looking for the tip of a hair on the moon. I mean, it's that precise. So it was unthinkable. And believe it or not, a lot of people even thought it's impossible. But then with the technologies that are advancing, it is now possible to detect them. So we could detect them. And now there are also like continuous wave searches. There are different groups which are looking for individual stars also. Like an extremely rapidly rotating neutron star, we say that it could emit a certain kind of wave. It's called R mode. So if you actually emit those waves, then we should be able to see them. And if we don't see them, that also gives us information. It tells us, okay, then probably there are some viscous forces inside the star which is damping out this mechanism. So every detection or non-detection even gives us some information about these objects from gravitational waves.
Yeah, that's science. It's always trial and error, I believe.
Right.
Yeah, and I think when all of us, like you, in general, your research group, when you deal with data analysis, I think the most important but difficult part of data analysis is to try and disentangle the actual signal from the object signal from background noise or systematics. And that's what, even I find it difficult when I'm doing my PhD. I'm just in my first year. So trying to do that is a very difficult, but also very important
challenge.
So and I can only imagine how that must be, especially in terms of gravitation physics and gravitational waves, because we have instruments that are highly sensitive, such as LIGO, but how difficult, I think sometimes people only look at the surface. Like if we, and if you, your research team or group tries to find detect gravitational waves, people applaud. But when you fail, they just randomly assume things which are not true, because only you know what kind of work difficulty goes into detecting these things. So how difficult is it to actually disentangle or differentiate these waves from noise in detectors such as LIGO, which are highly sensitive?
Okay, this is extremely challenging. Actually, I personally don't do it because I am mostly concerned with theoretical modeling of these objects, and so what I personally do is to develop these consistent models by starting from analytical calculations of the particles themselves, whether there are neutrons, protons, or some exotic particles you don't see on the Earth, and then how these particles would behave under very strong magnetic fields, under strong gravity, and then you calculate the structure under these very strange assumptions. What would happen if you have superfluid? So I take into account all of these complexities which are beyond our extreme properties that we know, and then we put these into the simulations, and then we predict data. I don't do it, but then I have students, PhD students and postdocs who are working on this, how to connect this with the data. Of course, there's a lot of data analysis that goes into it. Currently in the LIGO scientific collaboration, which is a huge global collaboration, there are different groups and people are working together to develop these tools. In order to, like, there are different waveform models, then there are there are two things. So first of all is to develop models which are themselves having all the information so that you're not missing out on some information, and then you match them with the observations. Yeah. And then the other way is the physics inference. Once you have the data, how you go back to the model themselves, right? So it's like you have to go back and forth in order to develop both fronts. Although I am myself not an expert on data analysis, but I depend on them in order to tell me how correct my models are.
That's right. But I think so. When you I think you said exotic, so that reminded me of your like early research work, which I think focuses on these very strange particles called hyperons. Right. I personally didn't know hyperons because that's something that is highly, I think hyperons are produced when the core becomes even more dense, like as you go into, like inside the star, right, as it gets dense. Yeah, and dense, I mean, we don't talk about hyperons over coffee. No, it's not common. Yeah, it's something you don't see here on Earth. Yeah. Yeah, I think it's something like when you go deep into the ocean, you're just thrown out there. You don't know what's there. And I think it's the same when you go deep into the star. You don't really know what's going on or what kind of composition the core has. And when your early research work focuses on neutron stars and trying to find hyperons, I mean, can you tell us what hyperons actually are and why going out after them? Like, why sort hyperons? Yeah, sure. So it's so these hyperons, yeah, I have actually, I mean, not intentionally, but I did a lot of work around hyperons. And the thing is, so these are actually, we call them exotic, although exotic is also a misnomer because it actually exists. So hyperons are these particles which are seen for a very brief time inside particle accelerators. So what happens in CERN or in LHC is that they collide these beams and then you have energies which are scaling up from nuclear to like extremely high energy systems, right? So in those systems, you see for a very brief period, these very strange particles appearing, and they are actually said to carry a property called strangeness. Okay, so what all the matter around us, they are composed of neutrons, protons, electrons, and these are not strange. They don't have that kind of property. But these hyperons have that property, and this only appears because hyperons are more heavy than their counterparts. So we don't see these kind of objects in daily life. And they also decay very quickly inside particle accelerators. Now, since they were found, people have always been wondering whether there are, I mean, on Earth, you just see them appearing and disappearing in like a very brief time. But are there any objects in the universe? Are there any systems, astrophysical systems, where they can actually stably exist? And the answer would be neutron stars, because you don't see any other system in the universe which is that dense. And this dense environment, it's like a breeding ground for hyperons. So now the question would be, it's like a detective game, how to find the signature of presence of hyperons. And you know why we ask this question? Because if they are actually present, they would change everything. They would change everything. They would make the star less massive. It might collapse earlier than we thought. Then it would give out maybe a burst of a signal, you know, because there is a kind of phase transition between a normal matter going into a strange matter. So now this opens up a lot of questions. Are we missing those signals? Because there are a lot of signals out there. You can see neutron stars not only in gravitational waves, you can see throughout the spectrum. You have these radio observatories, like these huge antennas you see. Then you have gamma rays, you see them in X-rays. There are all these telescopes floating around in space. They all see neutron stars in different color bands, you know, in different spectra. So now all this information put together, it's like a puzzle, you know, and then the question is whether we are missing out those signals which
actually tell us, which are there, telling us that, yeah, hyperons exist and they are very much there inside neutron stars. So this is a question that we are trying to, answer with all this data around us.
So it's a hypothesis, basically.
It's a
They do
hypothesis,
exist.
but yes. Now the question is, like, if they don't exist, the question would be why not? Because if we can even see them here momentarily on Earth, then why would they not exist in such a dense system? If it is actually not appearing, that would also like ask more questions than that. Why? Maybe it tells us something about the particle accelerators we have here on Earth. So it's like learning something new by observing it or not observing it. And and hyperons are one of the strange particles that appear. Even more strange brother of hyperon is quark, and these are very, very exotic things which appear at even higher energies. So these open questions are still there as to actually, if we have these kind of strange phase transitions, whether you can find these signals in the data.
And if these particles do exist, like subatomic particles to be precise, if they exist in the densest part of the star where temperature might also be very high, how do we actually probe? How can we actually probe into this interior part to understand these particles? Or do you actually need to probe into the interior to understand them? Or is there a way out of, a simple way out of this issue?
There is no simple way out because, the surface of neutron stars, for example, this is something we can still imagine because it's something like iron nuclei that are found in nuclear experiments. But then when you are going deep inside the core, this is like way beyond what we can imagine. And unfortunately, you cannot probe something. It's like, what we do in medical imaging. We try to go to higher and higher energy beams to see inside our bones, to see inside the cancer cells. So something like that. We are probing with different wavelengths, these neutron stars, but still it gives us information about the surface temperature, about a lot of things, but it cannot directly probe inside the core. And this is only possible with gravitational waves because it's like this lens which lets us hear what's going on right in the interior. So there's no easy way out. It's a kind of like a game where you have to do analytical calculations, and these analytical calculations have uncertainties because you are extending your theory to a regime where you don't know how it behaves. So you have parameters, and every time you have a model, then you compare these against the data, and this tells us a little bit about the parameters of your model. So you're like, okay, so I was wrong here, so maybe I can adjust it here. So it's like understanding back and forth, what's going on in these systems.
So your current, what are you working on currently? Is this based on the models for this, or is it something different?
So what I am currently working on is trying to understand how the composition inside the neutron star, if there are these exotic particles or if there are any other kinds of, strange phenomena, whether they are affecting oscillations. Like I just said, if you perturb a neutron star, you disturb it, then it will ring like a bell. It's like it's moving, and this will generate out gravitational waves. So if you imagine it's like a sea, and you throw a stone and there are these ripples in space-time, and we can actually detect them now. So now the question is how the composition actually affects these vibrations. And these vibrations, there can be many different modes, and LIGO scientific collaboration is looking for all these different modes. So we know a little bit about their properties because these modes are also there in the sun. For example, there are people studying solar physics, heliosismology. They are looking for those kind of perturbations. There are people working on astrophysics, stellar astrophysics. They also know this. Also, there are people working on fluid dynamics on Earth, and they also know about these fluid oscillations. So these oscillations should be there in neutron stars, and the signature of its internal composition should also be there. So we are looking for these signatures, and and there is a lot of complex modeling that goes into it, because there are a lot of like microscopic, macroscopic challenges that you have to take into account. So it's not a one-step game. You have to like go little by little, like every publication it's like an investigation. Okay, so this maybe, how does this affect the system? And then you say, okay, it does or does not, and then maybe you go a step further. So it just tells us a little bit more and more about all these different fields of physics that are involved in these complex systems.
Where does this mighty magnetic factor of magnetic field play a role in all of this? Because I think neutron stars they have immensely massive magnetic fields, if I'm correct. So
right.
What kind of problems do you face with this particular parameter when you simulate models, especially?
Oh, magnetic fields are like extremely challenging and extremely like exciting, because you know what happens is neutron stars are said to be very strongly magnetic. So there is even one class of neutron stars called magnetars. It sounds like science fiction, and these are ultra high magnetic fields. So normal neutron stars, they have magnetic fields which are already like way beyond 1,000 times beyond the most powerful magnets you can have here on Earth. And these magnetars actually are 1,000 times more powerful than that. And when these are so magnetized, they would create like outbursts and flares, so all kinds of crazy phenomena. You already know from the sun, right? The sun has flares, so you might have heard about solar flares and how it affects the Earth, because if you have solar flares, it actually even wipes out wireless communication here on Earth. So these are very energetic, and for neutron stars it would be like crazy. So it's like it's unimaginable what it can do to a star. And also magnetic fields are so powerful, they can even distort the star. It can make the star go from a spherical shape to a ellipsoidal shape to a toroid, even a toroid. I mean, how powerful is that? And it can like do crazy things to even like even at the end of gravitational wave, at the end of merger, so if you have neutron stars merging, it can even produce an object which is extremely strongly magnetized. So it's a challenge to understand how this would affect all the data and how it would affect the system itself. So it's a challenging field, but it's also very exciting.
Interesting. Yeah, it sounds like the magnetar sounds like straight out of a Transformers movie. But It's also exciting, like you said, because you get to actually ponder or think about the kind of new objects that it might produce, because magnetic field is, I think, important in case of every parameter. So
right.
I think we are running out of time. We need to have another meeting. It's already 40 minutes. It's going to
end. This is scheduled for only 40 minutes.
Yeah.
It said so it upgraded.
Yeah, now you have, it says includes unlimited minutes.
Okay.
So I think...
I'm not sure. I'm getting this notification running out of time.
Oh, okay. I don't get anything.
Yeah, I also got that it is extended to unlimited time. But in any case, I think if it stops, you can click on the same link and join.
Yeah, probably. Yeah. It doesn't stop now. So where does LIGO fit into all of this, and how important it is? How important is it for India to be a part of this huge collaboration? I think it's immensely important because you get to learn a lot of information from people like you. So how important is it that our country is actually, trying to planning to establish a laboratory here?
LIGO is the future. I mean, not only LIGO, I would say gravitational wave science is the future. I mean, we are entering now into an era which is called multi-messenger astronomy, because earlier, I mean, since the days of Galileo, you had only telescopes with which you could look at stars, and then anything that shines, you could look at it, and anything which doesn't, like most of the universe, so you could not observe anymore. And now it's like a stethoscope. You can actually listen in to these invisible objects, and each time you have a discovery, you find out something new. And this started with the discovery of the black hole merger in 2015, and then the neutron star merger came soon after in 2017, and it opened up an entirely new unseen universe to the world. Okay, so this is basically the future now, because even now that you have, if somebody was working on electromagnetic signals only, like looking at spectra, you would now even have to think about how gravitational waves would see it. Okay, so it's like it's totally giving out a universe that was unseen before, and this is also a very a great beginning for India, because we are involved in the LIGO-India project. And as you know, that the LIGO detectors in the US, in Hanford and Livingston, were involved in the first detection of gravitational waves. And for this, the three scientists who were involved in this project were awarded the Nobel Prize in 2017. And we are very, very lucky that now they are building the third detector, where one of the detectors from Hanford would be moved to Hingoli district in Maharashtra. So the groundwork is already going on, the base work is, and the studies are going on, which means that this LIGO-India project, which scientifically is also very important. Scientifically, it means that it will give, you know, like we need two eyes to see depth, so stereoscopic depth. So in the same way, with third detector in India, which is geographically distant from the US, we will now have the advantage of better sensitivity. We will be able to look at better sources, and also there will be an upgrade in the technology. So it's going to be an upgraded technology. We will be at an advantage to be able to observe better sources. And not only that, this upgradation of technology means that all the different fields in industry will be involved, because like I said, LIGO, gravitational wave detectors in general are a technological miracle. Okay, so they need the best technologies in vacuum, in suspension systems, to isolate all possible kinds of thermal noise and all possible kinds of noise. So you need the best lasers, you need the best technology in everything, which means that this is getting developed now in India in partnership with the industry. So this means definitely technological advance for our country. This means that all the scientists working on compact star physics, on gravitation, I would not say only compact star physics, because even recently there were tests of general relativity which were performed with gravitational wave data. So even anyone working on on theories of gravity would benefit from it. So it means that all the scientists who are involved in astrophysics would be encouraged now to work in this field. So this means a lot. So this means that India is now entering a new era in technology and in scientific research. So this is a very exciting time to be in for India. I think it means the future.
Already. Yeah, it sounds amazing already. So I was just wondering if there are opportunities where the general public, or maybe school students or undergrads and postgrads could, be a part of this, if this outreach program has such opportunities such as internships or maybe just workshops or seminars where we can take part.
Definitely. So I would say there are, if you're talking only about outreach program, definitely there is a lot to do in this field. So first of all, if you know that I started as a chairperson last year, and I have introduced a lot of different innovative outreach programs. So we have, if you go to LIGO-India.in, LIGO-India.in, you will see that we have a blog called Gravity Matters. And here you have a lot of students and researchers writing about the field in a very colloquial way. So even a high school student can understand most of it, or an undergrad can understand what is going on there from their own perspective, like whether it's data analysis, experiments, or theory. And then we also have many other things. We have a lot of events. We have also features about women, so who are working in this field. Then we have a podcast. So I would encourage all the undergrad students and postgrad students to regularly follow us on social media pages to be updated about what's going on. We also have from time to time announcements, like there are workshops that we are conducting, say about some data analysis. We recently had a build a detector workshop. So this was a fun workshop where students learned how to kind of concept build a detector. This was in partnership with UK, with Newton Bhabha. And so other than that, there are all these outreach programs, like we had an astrophotography webinar series. So there are a lot of undergrads, especially, who are very enthusiastic about sky watching and about photography. They learned about astrophotography. We had a contest in the end where we had absolutely fantastic, amazing pictures. So we will actually publish this very soon. So there are a lot of programs going on, and I would encourage, of course, you to follow them. And if you want to participate particularly in them, you can connect with us. And we will, of course, have some internship programs, but this would be more project specific. But other than that, also students are most welcome to participate. If you want even to interview someone, if you want to encourage someone to write about it, if you want to develop some scale models on gravitational wave detectors, there's a lot of fun stuff to do. So you can get in touch with the LIGO outreach team in that case. So that you're most welcome to participate. We are looking for all this enthusiasm in LIGO India.
That's right. Thank you very much for actually sharing this information, because this was most asked or requested. Not everyone is aware of what's going on. So I think it's important that you've told us now what is going on and what can be done as something from our side, from our part.
Maybe we should also highlight this more because this question also tells me that we need to highlight how others can get involved.
Yes, because I think there's a general fear factor on if you're capable enough, if I'm enough in general to take part in such a huge outreach program, be a part of it, am I enough? So that's kind of a hurdle that almost stops everyone in their path. So I think it's important that you highlight it's not something like that. Anyone can take part in all of that. So that's why I asked that question. But I think to end all the sciencey stuff, I just have one question. So in your research, what answer are you exactly seeking, or you're hoping to seek with what you're working currently?
So I would say science really doesn't work like that. I mean, the goal of science is actually not to find a particular thing. It is to, of course, we are seeking answers to our questions, but like I told you, even for gravitational waves, every new discovery asks more questions than the answers it finds. So this is what keeps science going, right? Because it's like, we learn more and more about the world around us, about the universe. And the fields all the different scientific fields are advancing at amazing exponential pace. And this is really exciting. But I think the goal of science is not just, like, oh, I answered all the questions, now I can go home and rest. No, it's not like that. It's just to open up new avenues. Maybe you discover even an entirely new field by looking at these objects. And I think all the scientists in the past have done that. They have not actually gone and looked for something. They found it because they were exploring. So it's basically the curiosity and the hunger to explore new things that keeps us motivated.
Yeah, that's very true. I think so. My mother, she actually, this is something that I always take with me. So she basically, it's not an advice, but what she said was, every person is a human, right? And it's despite the number of titles they carry, which may or may not be great or huge or fancy, they're still human. They're still a person just like any one of us. So to actually bond with them is to get to know the real, them. So in that sense, I think I'm very curious to ask you on how do you identify yourself other than or apart from being an astrophysicist, apart from being a researcher? How do you identify yourself?
First of all, I don't like stereotypes and tags, most of the time, it's like I get this very often. Like, I'm also a dancer, I'm also an artist, I do rock climbing, I do high altitude treks. I'm a very curious person. So every time I go to do something, people are like, oh, you're an astrophysicist and you also do this. So it's so stereotyped as to like astrophysicists can't be women, they can't be a dancer, they can't be something else. But I would say scientists in general are very curious people, which is why we are in this field. I mean, I'm curious and I'm very passionate about life and I am very curious about everything. And a lot of times, even the activities I do outside research, they tell me a lot about how things work and change my point of view. So, and also motivate me for outreach, because I learn about how different people think, and not only the way scientists think, there are different ways of thinking and analysis. So I personally don't like to describe myself as an astrophysicist or as a dancer or something like that. But I would just say I am a curious person who is very, very passionate about everything.
Yeah, exactly. That's the reason why I asked, because there's always this huge stereotype when you study science or physics or astrophysics now in general, that you do this, you cannot do something else, or vice versa.
Right.
And that makes no sense to any of us, because why not?
Why not?
Yeah. And because I see that STEM in science is a huge ongoing thing where all of us, have faced hurdles and discriminations, a lot which have been personal as well, but common in general. So what kind of, problems, or I would say hurdles or hardships that you had to face as a woman to reach wherever you are right now? There might still be ongoing issues, currently, because they never vanish. That's something
Tell
that we
me
can't
about it. Yeah, definitely. So this is a very, I mean, I could talk hours about this, but let's not go into like a complaint mode. But I would just say in general that, as a woman in astrophysics, if you are a PhD student, you probably are already facing this, and also others. I mean, even I think it starts very early, I think you should be mentally prepared to go through this. I mean, I would be surprised if nobody, I mean, I have actually interviewed a lot of women. Some people said they did not face any issues, and I was actually very happy to hear that.
Okay.
But in general, I think you should be prepared, because there are still a lot of glass ceilings that are to be shattered, and people have to go forward. So I have faced all kinds of discrimination. I have worked in many countries. I still work in global collaborations, and I have lived and worked in many countries. And although I have adapted very well, I speak many languages, I have adapted very well to those countries, but often I faced a lot of xenophobia and racism and sexism. Even in India itself, I face a lot of cliches about what a woman scientist should not to do. As a woman in society, what I should have done in my age and what I shouldn't. And there are all these, stereotypes and rules and regulations, which are actually not written anywhere, but people still, I mean, I believe only in laws of physics and no other laws. So I don't know where these come from. So there are a lot of, they impose their own views on you. And a lot of times I had to face where subordinates would not cooperate with me because I'm a woman boss, and these things are still there. And I would say you have to stand up for yourself. I mean, it could be in your family, it could be among your friends, it could be in the society, it could be in your office. You face discrimination. As a woman, I mean, naturally, there are a lot of women who are scared to raise their voice. But the thing is, you have to stand up for yourself, no matter how it is. I'm not saying like you have to become aggressive. That's not the point. But the point is that you can still try to be polite, but you have to be firm. You have to be firm. You have to be firm with your boundaries, because people often push your boundaries because you're a woman, and because of this and that, what they think you are. So you will have to set your own boundaries. You will have to learn to say no. You will have to stand up for yourself in society, in science, and stand for what you believe that you are capable of. I mean, people will tell you, oh, she can't do this and she can't do that. And nobody has done this before as a woman, blah, blah. And then you have to prove them wrong. But then first you have to believe in yourself and I mean, you have to stand up for yourself.
That's very true. Yeah, I was called overly ambitious. So I was very curious to know the kind of, I can only imagine the kind of things you must have heard, all of these years. Yeah.
Yes.
So what, I mean, like, in that sense, what, in your opinion, what do you think are the changes, if any, are needed in this education community or scientific community to kind of appeal more to women and future scientists or physicists in general, something that the system can do to bring about these changes?
I personally, of course, there are a lot of things which are very basic. Like, for example, astrophysics itself, there are a lot of astronomers who have to work in very remote places in the middle of the night. So there are things like, security, providing security for the women who are working in this field. And there are things like that. Of course, there are these basic things which need to be provided. Like, I have heard a lot of women who need childcare and financial support and things like that. Of course, there are all these basic things. But then more than that, I think what a woman needs is peer support and a lot of motivation, because you need to be prepared mentally, like I said, to fight it out. And then for that, I have discovered the power of social media recently. I have been doing science outreach for a while, but then particularly during the pandemic and during the lockdown, I found the power of community, and I found the power of social media in order to connect women, or in order to connect anybody who is being discriminated. Even a simple hashtag on Twitter can connect you to the entire world. So I feel that even if you feel you are isolated in a country or at home and you are not able to, assert yourself, then I feel that the community, as a community, we can provide support to women of all ages, whether it's an undergrad, whether it's a woman, a mid-career scientist, whether it's somebody who is struggling to find an avenue in research. So I think we can build a very nice support system through social media. And you are also doing a great job in this by, I try to do this in LIGO-India as well, by portraying women who are working in, it could be a master's student somewhere. And the thing is, what happens is that a lot of times this goes unnoticed, it goes unappreciated. And these people suffer from self-doubt and lack of motivation because of this. So I'm trying to portray these people who are at different points in their career and still trying to make it there. So I think it provides a lot of motivation. So we need to build on this community a lot more, I think.
Yes, very true. I mean, if there's something we can do I'd be happy to do it be a part of it as well, because I think it's something that's not being spoken out in a way that it's supposed to. It's always being suppressed, but now it's, we are living in the 21st century, so it's starting to come out, women's struggles in STEM. It's not just racism that we face or the gender differences that we face, but it's also hierarchical. Which makes no sense. But sadly, that's also a part of what all of us need to face, the hierarchy.
I also would like to say something. So this is something, because I am also in a lot of different associations which are related with women in STEM. And I see there is a big difference in the way earlier this was treated. This problem was treated, because of course women have always been fighting to get themselves heard. So I have met people like Jocelyn Bell and so on, who have of course stood up, and they have been given their dues, but way later than they actually deserved it. But so I understand these problems, but a lot of it earlier concentrated on complaints as to what should have been done here and should have been done there. But I am more a very optimistic person, and I believe in positive criticism. So I see a very massive shift now especially in the Indian youngster society, and I really connect with that a lot, is to to see what we can do. I mean, okay, we have been discriminated, that's it, but what can we do here to prevent it? And I think, so like, I would say, instead of like women getting together and whining about who didn't get what, I think what is more important is to stand up and provide a support system for others who are not able to do that right
Yes,
now.
very true. Yeah, yes. And
Even I
like,
would like to take this conversation forward. Yeah, like, in all of these years, like the people who have inspired me as being a boy, being a male, and not being a part of this woman, but yeah, in STEM, I have been inspired by a lot of women. And the first of all, it goes my mother. My mother is a science teacher, so she inspires me a lot. And then obviously Kalpana Chawla, and then we have Annie Jump Cannon. Well, I have read about them, and some of the best minds that I've seen in STEM are obviously women. So, I always support and I always encourage people through our handles. And then we have, so Shweta is also doing such a great job in the podcast, and we are surrounded by a lot of women. And now they're my colleagues, and they had been my inspiration. Yeah.
A big shout out to the guys who stand up for
yeah, that's true. That's
equal
very true.
rights. No, that's very true. Yeah, I mean, this is also something. I think awareness is also important, because a lot of men didn't even know that discrimination existed. They think, sometimes I know scientists, I have met colleagues who made a very sexist statement and didn't even realize it.
Yeah.
They thought it's so common that it was actually extremely discriminatory. So we have to make people aware as to what your, how you behave even can make a big difference in people around you. And I mean, of course, a lot of women have inspired a lot of other girls and other men. So it's for me, I believe in inclusion. So it's not about just women; it's about inclusion. About I mean, no matter what color, sexual orientation, whatever you have, if you are feeling discriminated, I think that's something we need to definitely work on to prevent it. I mean, we need to be neutral, gender neutral. We need to make it, like not have these stereotypes for people that you cannot come from this background, you cannot come. I believe in inclusion and putting people at the same level.
Yes, that's very right.
And I think for people who are who think they are not facing discrimination should also look around them and see that if there is anyone around them and who need their support. I think this is very important.
Very true. I think it's more about not turning a blind eye to these issues. Like if they don't relate or concern to me, you just turn a blind eye. It's not about that, but rather than addressing and looking at what's going on around you as well. That's very right. You're right. And I think one major important question that I personally wanted to ask you is, as a first year PhD student and a PhD student in general, you must have gone through this imposter syndrome, or you might still be going through imposter syndrome at any point in your life or research work, because research, I wouldn't say it's a lonely field or a lonely work, but it's something that we love and do. But it can also tend to, get isolated or lonely sometimes, because you tend to work on your own at certain points in your work. So how do you, or did you get back on track? How do you overcome this imposter syndrome? The feeling that you're not
self-doubt, is it?
Yeah, I mean, like I don't deserve this position, this PhD, this work. Like I'm not doing enough to, be a part of the scientific community. Those kind of thoughts that people have in general.
I don't think I really suffered from self-doubt. Okay, I would put it this way. So let's see that there have been phases when I felt that I could not achieve what I was capable of my potential. I was not doing enough, justice to my potential. I did feel like that, but I don't think. Sometimes, even not only first year undergrad or whatever, you could be in your postdoc. A postdoc time is one of the most mentally challenging times, because you often move to a new country and you are starting off, you start off on a different ground, because other people coming from other backgrounds, you see, oh, they are very good at computation, they are very good at something else. So where do I stand? So of course there are challenges like this, and I would say that take your time to work on yourself. I mean, allow yourself, to, I mean, it should not affect you mentally in the sense that I'm not enough. That feeling should never come. You can say, oh, okay, this person has had this opportunity, which I did not have. This person is better than me. Appreciate them for that. And tell yourself that, okay, if this is something I need for my work, I will work on it. I will work on my defects. I will take time to build on it. Trust the process. I mean, trust the process in the sense, okay, don't think I'm not good enough. I'm not good enough because I have not learned it. I have not mastered it. I have not I'm not there yet. You can tell yourself that. So even like just last year when I started off as a faculty, of course I was new, and I started off where, I mean, I'm the only woman faculty in IUCAA, so there's nobody I can go and ask like, oh, how should I do this? How should I do that? I have to figure it out, and I will make mistakes, and this is okay. And I like to do things differently, so I usually don't go around asking people how they did it. I try to figure it out myself. So allow yourself that time to build on yourself. Don't just go back home, feel depressed and like, oh, I didn't do enough, I'm not good enough, I will not make it. No, it's not that. It's like something like you note down for yourself and set yourself a goal. Okay, I will do this in so many months. Work on it. Give yourself the time. If you think you're not progressing, go back and review what is the process you're following. Maybe you need to change your technique. You need to approach someone for advice. Go out there, because especially now because of the pandemic, I see that everything has opened up. Earlier there were these boundaries of countries and this and that, and now you are sitting in UK and you're interviewing me. You can reach out to anyone. So go out there, talk to people, learn, and never give up. I think in science it's a bit like mountaineering. It's like, oh, if you're already starting with self-doubt, you will never reach the peak. No, you just have to. It's going to be tough, but you just have to tell yourself, I will get there, and work on what you need to get there. So
yeah. Okay, yeah, that's actually very true. But I think, like, just two more questions to finish off. The first is, if you have any, can you share one of your defining moments or a turning point as an astrophysicist in your research work?
In my research work, I would say there were several, stepping stones. So one of them was, of course, like you said, so I was struggling during my PhD days, and I was just writing papers, and I was not sure where this is headed. And then when I finally got the Alexander von Humboldt Fellowship, which is a very prestigious fellowship from Germany. And it's not only something which is like for a couple of years, it's something that is there for your entire life. It's a very prestigious fellowship, which basically puts you in connection with the German research scene for your entire life. So so this was something, of course, which was a turning point in my research. Another thing I would say was, of course, getting the faculty position at IUCAA and LIGO-India, because this is something that gives me the opportunity to do the research I want personally, and also to do outreach, which is also something about that I am passionate about. If you talk about turning points or milestones in outreach, there was a point also in France when I was a postdoc there, and I was selected as an ambassador for science. So this was also a very big turning point in my outreach career, because it was strange that I was selected as an ambassador for science because I was the only non-French person, not from Normandy. So everybody else was from there, and I was a foreigner, and they actually chose me because of my international experience and the fact that I was from somewhere else and I was performing research in Normandy. So it told me the power of outreach, and that even you as singled out, you could be important to as a role model where you are standing right now. So yeah, I think these points were very important in my life.
Yeah. Okay, that's really amazing. I mean, yeah, I think it inspires not just us here, but also everyone when they listen to you speak and tell us about these important points. But to finish off, I think there's one important thing that I think we should also, and you should also address, which is I think often it's not just in our country, but I would say everywhere in general, commonly, people always have this assumption of choosing a position, not just say a degree or master's degree or PhD, postdoc in general. It's always on reputation. So they look at the reputation of the universities, like, world ranked, ranking, and all of these reputed, professors, which makes no sense to me, because when I transitioned from my master's to my PhD, so I did my master's in the UK. So we actually had to have a talk, like a seminar, my entire department, where the professors straight up gave a presentation, which is very weird, but they had to present, and they told us that, look, when you go on to a PhD and further to your postdoc, reputation does not matter. It's more on choosing what you actually like the project and the right supervisor, because you can be in a world ranked university and still have, I wouldn't say a bad supervisor, but a supervisor who's not supportive as you would imagine him or her to be. So, and when I've spoken to most of my friends who are still doing their master's or undergrad, they've always asked me about this hierarchy, like this reputation, MIT, Oxford, Cambridge. And I just laugh it out, because now that I actually know and I've experienced how it feels like, I thought it would only be right for me to ask you, because you're even more, than all of this. So you would have a better idea to answer this question.
I think, okay, I don't want to impose my views on people. Of course, people have their own way of, people are free to choose their life decisions. I personally, I am a black sheep in society. I've always done things the wrong way. So it's, I have had also a lot of friends like this who had their entire life figured out when I started, and I was completely clueless. And I can tell you none of them are in physics research right now. They all fell out of the career ladder, and I'm still here so far. So I don't think all these formulas work. If it works for you, that's great, but for me, it never worked. And it's funny because a lot of exams that people told me I should have given, I never gave. And actually right now I'm an examiner for a lot of them. A lot of societies people told me to join. Now I'm invited to join them. A lot of very famous researchers who people told me I should go and talk to, they are actually working with me right now, and I have not made any effort. I have just worked on what I loved and I'm very passionate about. So people find me. And I can tell you a very funny story. So I was attending a conference in Vancouver, and this was like very early in my PhD days, and I was very much lost. It was a huge conference with very famous people from cosmology and astrophysics. And anyway, so there was a lunch break, and I was a bit late to get out, and everybody had left, and I was trying to figure out where to go for lunch. And I remember there was an old guy standing there, and he said, "Oh, are you left out? Do you want to go for lunch with me?" And I said, "Yeah, sure." So we went for lunch, and we had a very nice conversation, and he was like, "Oh, you're such an interesting person, blah, blah," and so on. And then we went back to the conference, and in the evening we had conference dinner. And so one of these friends of mine who had it all figured out, he was already calculating who he should sit next to, which would get him, the right entry to the right university. I don't know what. I was just like fooling around. And then this guy walks up across these 100 tables, and then he starts talking to me and sits down next to me. So I see my friend like he's gasping for breath, and then he comes up and says, "How do you know this guy?" I said, "Oh, we just had lunch today." And he said, "Do you know who he is?" So he's a Nobel laureate. So I was like, okay, so what? But I mean, I did not calculate, like it just happened. And I think he enjoyed so much the conversation because it was so candid and it was so natural. So it was really funny. And and he often came back to talk to me. And it's funny because a lot of people were actually trying to talk to him. So I don't think these things matter. And the guy I'm talking about is actually fallen out of physics. So no, okay. I don't think these things really work. I mean, in the sense, of course, you should talk to people. Building network is important. In the sense, you should not. I have seen a lot of people who are forcing it, like at the end of every seminar, raising their hand and trying to ask very intelligent questions. No, I don't think it works like that. If you are really good, if you're really motivated, passionate about your field, and you're working on it, and you talk to people in general, everybody, it will build you a good network. You don't have to force it. You just open up your avenue. Sometimes I have met people who are in a completely different field in a conference dinner over just talking over things, and years later it led to a completely different collaboration between completely unrelated fields. So I don't think the universe works like that. I don't believe it. You can, of course, I know that some people have had they have advanced in their career by taking very calculated paths, but I personally, I believe you let things flow and you do your best, and you always you love what you do and you're motivated by it, then the universe will find a way for you to do what you love to do.
Yes, that's very true. I think it's sometimes most random and casual conversations with such heavy and high professors and Nobel laureates is what gets you in this sense, like in, but usually what actually makes you stand out rather than having in-depth scientific talks, because that's when they get to know the real person. Like, you have to know who you're going to be working with if they take an interest in you. And that's, very important than the scientific knowledge or, jagra that you have in your head. So the real person is what matters, I would believe. And as you rightly said, I think that's why, I think he would have found you more interesting because he got to talk to you and get to know you personally.
Yes.
That's very
that
cool.
reminds me of a funny incident. So there was a conference in Orissa, and there was a famous German professor who was there. And I remember one girl walked up to him and said, "I want to work with you, blah, blah." And he started talking about completely different things. And he said, "Can you tell me the Dash avatars?" And she couldn't. And I remember he didn't work with her.
Okay. Yeah, that's very true. I think even supervisors are like that. Mostly when you have these interviews for projects or positions, they don't really ask you about. There are obviously certain professors or supervisors who turn that interview into a very intense oral exam kind of a environment. But there are also people who have a balance between both, so they know
Definitely.
that getting to know the actual you, like what you're capable of and what your weakness is, which is very important, not just your strengths, is what I think that's how they decide whether you're fit to be in their research group or fit to work with them in that in the scientific environment in general. So that's something
I always stress on work-life balance. Even with my students, I always emphasize on that, because you cannot be motivated in only physics and not look at anything else.
Yes, very true. Yes.
It's very important.
Yes. Yeah, I think that's how to finish it off. I just wanted to ask you about this, like, where do you stand on this whole reputation and all of this thing that's going on with students, especially these days? I think it's kind of like a stigma, not a social stigma, but like a mental stigma, where they feel the need to be at the top at choosing these reputed world-ranked universities, and only then will they be able to be identified or propel in their career. That's kind of some stigma that I've always found. I think I have
also had colleagues who have worked on projects with very famous scientists, and they have not got anywhere. So
yes, exactly.
Yeah, it's not necessarily true. I would say it's good to have a break, because I have worked with very famous people, and they are, famous for a reason, because they have a very strong analytical capability, which you learn from, and you also learn very efficient techniques, how to approach a problem. So it's important also, but it's not necessarily the key for success. It's basically up to you. You could even learn it from I know people who have been more motivated by a teacher in a village than they have been by a Nobel laureate. So I think it's where you find your motivation from, and the world is now open. If you want to learn better techniques and more efficient ways, you just observe and you learn and you try to improve yourself.
Yes, you're right. I think it's a learning curve. Nobody starts out knowing everything. It's a step-by-step process, like you said. To finish it off, do you have anything that you would like to address or tell? Anything, any important issue that you find a need to be told or addressed to people who are watching or listening?
Maybe I would put a message like I said, because of my time constraints, a lot of time I get messages from a lot of students. I feel bad that I cannot go back and reply to all of them. I will try to see how to do this through LIGO-India Outreach, but in general, if people are trying to reach out to me and I cannot personally get back to you, my message would be that please don't be demotivated. I mean, there are a lot of students who ask me like how to get into gravitational wave science, how to get into astrophysics, what they should study in school, and so on. I mean, it's for me, unfortunately, I cannot go and write to everyone and answer in detail, but I would just say keep an eye on the subjects you are offered, try to do better in them, try to learn them. It's not that, like you said, going to a very great university or school will necessarily ensure your success. So try to do your best wherever you are, whichever point in your career you are, try to learn and keep an eye on opportunities on the different social media channels. All mega science projects have these. So try to learn what are the opportunities, try to apply for summer projects and internships and different opportunities. There are a lot of summer schools which are going on online. There are lots of lectures online. Whichever interests you, you can go through them. Don't force yourself. I mean, there's okay, I am like 16 years old and I want to learn do a thesis. It's not like that. Trust the process and try to do your best. Don't burn yourself out. Learn, keep your ideas on opportunities open. I mean, some people even ask me, how can I get into LIGO India? I would say when you grow up, you will figure it out. You will figure it out because you will see where LIGO is. I'm also part of Einstein Telescope, which is the next generation. So a lot of things are developing, and by the time you are at that point in your career, you will figure it out. Just keep yourself open to what opportunities are there around you. Don't be demotivated. If you really want to be a scientist, I would wish you the best and keep going for it. That's my message.
Thank you very much, Shahid.
Just before we end, we offered people to ask you questions on our Instagram and LinkedIn. So we have shortlisted some of them. So I'd like you to answer on behalf of these people. Then how important, this question is asked on Instagram by Rashmi, and this question is, how important is it to know a culture, their heritage and nuances before carrying out local and even university level outreach activities?
Hi, Rashmi. I know Rashmi very well. She also is one of the volunteers for some of my LIGO-India projects and a very good science communicator. So thanks for the very interesting question. So this is actually very, very important, what you just said. And I'm surprised that you asked that because it's something that I have learned living in different countries. So outreach in Germany is different from outreach in France, is different from outreach in India. And also LIGO-India project itself, you have local level, you have to go, you have to think about schools around the site in Hingoli, which is a village, a remote village. Then there are national level institutions, research institutes working on it. There are international collaborations. So you have different people from different backgrounds who are connecting to this project. And it's very, very important to understand their mentality in order to do outreach, because you have to basically speak their language in order to make them understand. And understanding the culture definitely helps with this. So this is one of the reasons I speak so many languages. And so once you know the culture, the language, you understand how the people feel, what they are passionate about, what they connect with. what are their sensitive points, so you understand, and then you can actually talk to them in their own language. And so scientific outreach is not only about giving out information, it's like to tell them how passionate this particular science field is, and to make them understand what contributions they can do, or how they can be involved in this project. So it's very, very important, I think, to understand the local sentiments. Yeah, thanks for the very interesting question.
Okay. So now this question has been asked by Deepan, and it is, if you had the option to give advice to a younger version of yourself, what would that be? What would that be?
Oh, cool. Nice question. Yeah, actually, if I think this goes a little bit around what you just asked me. So I would say, if I already knew that I would survive out this difficult academic journey, then probably I would have taken it, I would be more chill, because I would think, I think that's what people should do, take it easy, because people, what happens is that it's the uncertainty of the future that makes you very stressed out, like, what do I need to do to get there? But then now that I know that, yeah, I did survive it, and I was always doing it right. I mean, although, like, self-doubt creeps in, and you think like, oh, am I going to survive? What am I doing wrong? And why am I not where I should have been? And so I think I would have told myself to take it easy and enjoy the process, in trust and enjoy the process.
Okay, so there are some questions that we have already been answered, like how to involve in LIGO-India project, and how you can overcome anxiety while working as a researcher. So thank you for your questions, Simran and Anu. Yeah, thank you for your questions, and I think this was the end of this episode. We'll have such more conversations in Hello Astrophysics. In Hello Astrophysicist segment, which will be starting now on. This was the first episode of this. Thank you for participating, Shweta, and thank you for joining us, Debarati ma'am. It was an honor to meet you.
Thank you very much for this opportunity. I had a lot of fun connecting with you too. And, all these conversations was really peppy and fun. So keep up your good work. I hope there will be more interesting conversation with other astrophysicists. I'm also eager to hear about it. And yeah, so keep yourselves motivated with the great initiative you have started. And yeah, I'm really happy to be here.